Okay, Assalamualaikum warahmatullahi wabarakatuh. So this video is a pre-recorded tutorial session, which in this tutorial session I will give you an idea on how to solve all of these case study under tutorial 1 or under chapter 1, Principles of Mass Transfer. So we go to the first question. The gas of carbon dioxide is diffusing at steady state through a tube 0.2 meter long containing nitrogen gas at 298 K. The total pressure is constant, which is 101.32 kPa, and the question gives you the partial pressure of CO2 at one end and 456 mmHg and 76 mmHg at the other end. So this will be partial pressure of carbon dioxide at point 1, and this is the partial pressure of carbon dioxide at point number 2. And the value for diffusivity coefficient is being given in the question, which is 1.67 multiplied with 10 to the power of minus 5 meters square per second for that condition. And the question asks you to calculate the flux for carbon dioxide for equimolar counter diffusion. So for this kind of case study, the keyword is the equimolar counter diffusion. So we need to take note that by referring to this case study, we need to identify what is the final equation that you may choose in the appendix. So because of the equimolar counter diffusion, if you refer to your appendix, to calculate the flux, you need to pick this first equation. JA is equals to DAB over RTZ multiplied with partial pressure A at point 1 minus partial pressure of A at point 2. So the first equation stated in the appendix refers to the equimolar counter diffusion case study. For the second equation in the appendix chapter 1 refers to the one component diffusion. So we need to take the first equation to solve for question number 1. So copy back this equation into your answer script, okay, and then you need to extract all of the information given on your paper. So normally I advise you guys to draw the diagram of the tube as well as putting all of the information on that diagram. So normally for that kind of case study, what you need to do is to draw a tube, for example, okay, and then put all of the information given from the question on the paper. So okay, so the question gives you the partial pressure of A at point 1, okay, which is, if you refer to the question, okay, the question gives you the partial pressure of CO2. Okay, sorry, before that, okay, before we extract all of the information, okay, firstly, you need to assume first what is component A and component B. So you just write down, let CO2 is A, and the other component which is stated in the question is nitrogen, right? Okay, so let nitrogen would be the component B. Alright, so whenever we know that this component A is carbon dioxide and component B is nitrogen, which is, we know this is the binary mixtures. So what you need to do is to extract info from the question. The question gives you the first from the first sentence, they give you the gas of CO2 is diffusing at steady state through a tube 0.2 meter long. So this will be the Z. Okay, so the question gives you the Z. So for example, this is the Z. Okay, so the Z given is 0.2 meter long, 0.2 meter. Okay, right, and then what else? The question gives you the total pressure is constant at 101.32 kPa. So the total pressure is given, so write down in the under this condition, pressure total is P capital 101.32, okay, to 2 kPa, right? Then the partial pressure of CO2. So CO2, we assume CO2 is component A based on the assumption. So at one end, meaning this is the first PA and then this is the second PA. So this will be PA1 and this will be PA2 at point number 2. So 456 mmHg. So this will be, there will be PA1 is equals to 456 mmHg, and the second point here, point number 2, is PA2 is equals to, what's the value? 76 mmHg. 76 mmHg. Sorry, Hg. Alright. So basically, the first point is we know that the partial pressure will move towards the lower partial pressure. So that's why this point is point number 1. Okay, so this is point number 1 and this is point number 2. Okay, so we know that the diffusion process will happen starting from point 1 to point number 2 is because of the value of the partial pressure itself, which is higher to lower partial pressure. So the movement of the flux will move from point 1 to point 2 for component A. Okay, and then what else? The question gives you the diffusivity coefficient value. Diffusivity coefficient value, this value DAB. Okay, so DAB is the constant. Okay, DAB equals to this value, and then the question also give you the temperature. So put the temperature value to 98K. Yeah? Okay, the temperature is equals to 298K. All right. Okay. And then the question asks you to calculate flux for CO2 for equimolar counter diffusion. So for equimolar counter diffusion, the value of flux will be in terms of J. So calculate the flux for CO2. CO2 is component A, so it will be, the question asks you, okay, to find J. The question asks you to find J A, right? J A, the flux. Okay. So this is the all of the information given from the question, and we notice that the equation that you need to pick in the appendix is this equation, okay, to calculate flux, right? And then you put in your statement or in your oops, does it appear? Okay. Okay, copy and paste here. Cannot come. Okay, basically you need to use this equation. Okay, use this equation, and then you just need to substitute all of the information that the question already give it to you. Okay, and then substitute into this equation, because we already know the value of DAB, you already know the value of T, Z, PA1, PA2, and or you can get it from the and you already get the value of R from the ideal gas law value in the appendix, which is stated here. Okay, so this is the list of gas law constant, which is R. So how to pick which value R that you need to choose is you just refer to the unit that the question applies for DAB, for partial pressure, and so on. So if you see, the most related R value is the last one, because it is in terms of Pascal, it is in terms of Kelvin. Okay, so you may take this value 8314 to be substituted into the equation to calculate um, the flux. Okay, but make sure the unit must be standardized first, meaning the R constant here that you pick is in terms of PA, but in the question they give you the pressure total in terms of kPa. So either you need to standardize the unit all to be PA, or you need to divide with 1000 of R constant to be in kPa. And please don't forget, when you want to substitute into the equation for calculating flux, for one component steady state equimolar counter diffusion, you deal with in terms of partial pressure, right? So the R constant, the pressure unit contained in the R constant are in PA. So by right you need to uh, change the unit of partial pressure which has been given in the question, which is in terms of mmHg. You need to convert it to be the in terms of Pascal. So either you want to use you do the conversion using your calculator, or you may refer to the appendix, which is stated in the second last page of this appendix. Okay, which is in terms of pressure. So you may use any of this information to change the unit of pressure to make sure all of the units standardized before you press on your calculator. Because in order for you to get full marks for this kind of question, whenever you write down this equation in the paper, and then you substitute all of the information given from the question, and then you need to do the unit cancellation. You put all of the values and all of the converted values, which is the unit is similar, and then you need to do the unit cancellation in your solution, and then finally you press your calculator carefully. You get the final answer, and please write down the remaining unit after you do the unit cancellation. Then you will get uh, the 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 final answer for this question. And the final answer for this question, you may get the value of 1.070 multiplied with 10 to the power of minus 6 kg mole per m2s. So this unit belongs to the flux unit. Okay, right. So this is the idea on doing the question number 1. So let us move to the question number 2. In a gas mixture of CO2 and hydrogen, okay, hydrogen gas, steady state equimolar diffusion. Again, this is equimolar counter diffusion. So we know that when it goes to equimolar counter diffusion, the similar equation you may pick in the appendix to apply for the case study. The first equation is occurring at the pressure of 100 kPa. So this is the total pressure. The total pressure given is 100 kPa, and the question gives you the value for temperature. Okay, and the question give you partial pressure of CO2. All right, so basically how we want to assume which component will be A or B. The first equation that you see is normally will be the component A, and the second component that we see is the component B. So this will be the 0.01 is the Z, or the elevation, or we call it as the distance or length of the pipe. And then with refers to this sentence, okay, it stated the partial pressure of CO2, which is the partial pressure of component A, at one point to another point. So how can we know this is the partial pressure of component carbon dioxide or component A at point 1 is because we know that in order for the molecules diffuse, it must start from higher pressure to lower pressure. So that's why this will be PA1 or P partial pressure of carbon dioxide at point 1, and this will be the partial pressure of carbon dioxide at point 2, PA1 and PA2. And then the question give you the flux of hydrogen. Okay, so this is the since we deal with equimolar counter diffusion, so we will use the flux as J. Okay, if you recall back, okay, if the case study is one component diffusion, the flux denotation is normally write down as N. Okay, but this one is for equimolar counter diffusion, so the flux will denote as J, but the question give you the JB value because the hydrogen is component B. The question did not give you the flux for A. So this value minus, okay, minus 1.6 multiply with negative 5 kmol or kgmol per m2 second is the JB value, and the question asks you the value for DAP, diffusivity coefficient. So meaning that, okay, it is not necessary, it is not always the question asks you to find the flux or J. The question may also ask you to find the DAB. For let's say for the question number 2, the question asks you to find diffusivity coefficient and they give you the value of flux. So for this kind of question, we apply the same practice, which is you write down all of the particular details or extract all of the information in this kind of diagram, and then you put the PA1 value and PA2 value, the length, and all of the particular details. But the thing is, the difference is for question number 2, they give you the value of J. They give you the value of JB, okay, is equals to something, and then they ask you to find DAB. Okay, so they ask you to find the value of DAB. So first thing, okay, after you see the question give all of the values in terms of CO2 is component A, right? So 15 and 5. So we just edit the first information here. So this will be PA1 is equals to 15 kPa, and this is for question number 2. PA2 is equals to 5 kPa. All right. And then the question gives you the flux, but the flux stated here is JB. Okay, so when you see in the equation, okay, this is already being given in the question, DAB. R, we can choose it from the appendix. T is from the question, which is 20 degrees C. Z is also being given in the appendix. PA1, PA2 also given, but the question asks you to find DAB. So you write down this equation first, rearrange this equation, make DAB as the subject. So it will be DAB is equals to JA multiply with RTZ over PA1 minus PA2. So make DAB as the subject, and then, okay, this JA, okay, we don't have the value of JA from the question, but the question gives you the value of JB, right? Okay, so JB value here, okay, is actually according to the rules of uh, equimolar counter diffusion, JA is equals to minus JB. So you can substitute, okay, the value, and then you will get the value. Okay, so the question gives you the value of JB is minus 1.6. Okay, that's the question. Question gives you the value for JB. Okay, this value. Okay, so in order for you to substitute the value inside the equation, there must be in terms of JA, right? So according to the equimolar counter diffusion law, JA is equals to minus JB. So it will be is equals to minus multiply with this value. So it will be positive value, right? Minus multiply with minus. Okay, so this is the value for JA. Okay, so this is the value for JA. So after you get this value of JA, you substitute into the equation that you already rearranged before, and then finally you will get the value of DAB. Okay, and the value of DAB that you will get is 3.9 multiplied with 10 to the power of minus 5 m2 per s. And as usual, in order for you to get full marks, after you do the rearrangement of the equation, you substitute all of the values inside the equation, and then you write down the values together with the units and shows the unit cancellation. And later on, finally, you write down the final answer of DAB together with the remaining unit, okay, which is M2 per S. Then you will get the full mark for that kind of case study. So that's the idea on how to solve for question number 2. So we move to the question number 3. Ammonia gas A and nitrogen gas B are diffusing in equimolar counter diffusion through a straight glass tube for 2 feet at 298 K and 101.32 kPa. Both ends of the tube are connected to large mixed chamber. The partial pressure of Nh3 in one chamber is constant at 20 kPa and 6.67 kPa in other chamber, and the diffusivity coefficient is given. So if you recall back in the slide notes, okay, there is a slide shows you the two chambers connecting with a long pipe, and then I've stated there several equation used under equimolar contour diffusion. Okay, so for the question number 3, okay, you just imagine that there is a two large chamber. Okay, there is a two large chamber. Oops. Okay, two large chamber. This will be chamber number 1. Okay, and this will be chamber number 2. Alright, and this two chamber is connected with a long pipe. Okay, so I just assume there is a pipe connected to two large chamber. Okay, so this is kind of case study. And then extract all of the information. So it already stated ammonia gas, it will be the component A, and nitrogen gas will be the component B, and it is stated equimolar counter diffusion, right? So we will use the first equation again, okay, because this is equimolar counter diffusion equation. And then what else? The question give you the information 2 feet long. Okay, so a straight glass tube, or the pipe is, the tube is 2 feet long. So in this diagram, so this is the Z value. Okay, this is 2 feet. All right, and then the question give you the temperature 298 K, and then the pressure is 101.32. 298K 101.32 kPa. Okay, and then the partial pressure of NH3. So NH3 is component A, so PA. So PA, this will be PA1 and this will be PA2 because the higher partial pressure would be the PA point 1 and this will be PA point number 2. So in this diagram, this will be PA1 is equals to, what's the value? 20 kPa, and this would be PA, oops, PA2 is equals to 6.666 kPa. 6.666 kPa. Alright, so back to the question, and the question gives you the diffusivity coefficient. Okay, so this value, diffusivity coefficient. Okay, and the question gives you DAB is equals to this value. Alright, so back to the question. Calculate the diffusion flux for NH3. So the NH3 is A, so flux. Flux for equimolar counter diffusion is not denotes as J. So A asks you to find, okay, A asks you to find J A. Okay, so how we need to solve this one? It's very easy, as we know that it is equimolar counter diffusion. You copy this equation onto your paper, and then you substitute all of the information given from the question inside this equation. Again, repeat the same thing. Put the values, put the units, shows the unit cancellation, and press the calculator carefully. You will get the final answer together with the remaining units. Then you will get the value for the first answer. The answer is, answer is 2.031 multiplied with 10 to the power of minus 7, and this is the unit for flux. And then, okay, for question number B, calculate the flux for N2. So flux is also J, but it is for JB. So we know that the fundamental of diffusion process for equimolar counter diffusion, the rules of thumb is JA is equals to minus JB. So whenever you get the value for JA from the question A, you can find out the P value. It will be the value of JA, you multiply with minus 1, and then you will get the value for JB. So it means that JB is equals to minus JA. So minus 1 multiply with the value of JA that you get over here, then finally you will get a value for JB. So that's the simplest way. But you may also calculate the JB by using this equation, but you need to change all of the information here to be the component B information. So this will be DBA, but shares the same values as the question provide to you, because DAB is same with DBA. So you just replace the value of DBA inside this equation, and then this will be PB1 minus PB2. No longer use PA1 minus PA2 if you want to calculate for JB. So how can you get the value for PB1 and PB2? Is actually by using Dalton's law, because the question already gives you the value of A value. So how can you find the value for PB? So it is very easy. It's just apply the Dalton's law. It will be PA1 plus PB1 is equals to P total. So after you get the P total, okay, you may rearrange this value, this equation to make PB as your subject. So it will be pressure total minus PA1. Then you will get the value of PB because pressure total being given in the question, which is 101.32. PA1 is also being given in the question, which is 20 kPa. So then you will get the value for PB1. Same goes if you want to get the value for PB2. Okay, so PA2 plus PB2 is equals to P total. So this is the rules of fundamental of Dalton's law. So whenever you want to get the value of PB2, it will be PB2 is equals to P total minus PA2. So pressure total, use the same value of pressure total here, 101.32 minus with PA2, which is 6.666 kPa. Then you will get the value of PB2. So as you get the value of PB1 and PB2, substitute into this equation, PB1 and PB2. Finally, you will get the value of JB, and you will get the same answer whenever you apply the equation like JA is equals to minus JB. You will get the same answer as you substitute the info into the equation for fixed law or to calculate JB. Okay. So the answer that you may get is actually the same answer but with the negative sign here. Alright, so the last question for question number 3, calculate the partial pressure of NH3 at a point 1 feet in the tube. So partial pressure of NH3, we know that NH3 is A, so this will be PA, but this PA is for 1 feet long. Okay, so according to the diagram, according to the diagram, we already draw the diagram for 2 feet. So the idea is they ask you to calculate the partial pressure of A, okay, when the length of the pipe is only 1 feet. So the idea is actually we split in the middle of the tube here to be in 1 feet only. So for example like this, okay, up to the middle of the tube, which is just 1 feet, okay, 1 feet, and then there will be a chamber up to 1 feet, another chamber. Okay, so this is the idea. Okay, so this will be the chamber number 3. Okay, chamber number 3. So the question asks you to find partial pressure of PA3 lah, because this is chamber number 3. If PA2 for chamber number 2, PA1 is for chamber number 1. So the question just put the sentence like calculate the partial pressure of NH3. Okay, NH3 is refers to partial pressure of A at chamber number 3. Okay, so the question asks you to find PA3, what's the value? Alright, so for this kind of case study, okay, as you want to calculate the value of PA3, and and it is equimolar counter diffusion, so still we need to apply this equation. Okay, so JA is equals to DAB RTZ multiplied with PA1 minus PA2, but we know that the movement of the molecules will start to move from point 1 to point 3, right? You just neglect the point number 2. So it is just between chamber 1 and chamber 3. So the partial pressure will move from PA1 to PA3. So that will be some manipulation of this equation. This will be PA1 minus PA3. Okay, and still you are going to use flux for A because we deal with component A. Why we need to remain as component A is because the question asks you to find partial pressure of component A, which is NH3. So by using this equation, okay, as we replace, this will be the PA3, yeah. As we replace, this will be PA3 value. For example, okay, I change to this PA3. Okay, first thing, okay, as we know, we need to calculate for PA3. You rearrange this equation first, make PA3 as the subject. So meaning JA multiply with RTZ divide with DAB, and then PA3 is equals to that value multiply minus with sorry P in PA3. When we go to the left hand side, it will be positive value, and the value for JA multiply with RTZ over DAB, okay, must be subtracted with the PA1. So PA1 minus that value to and put it in the right hand side. So PA3 is equals to PA1 minus JA/RTZ over DAB. So you need to rearrange this equation first according to the mathematical rules and make PA3 as the subject, and then put all of the information in that question, in that equation, and then finally you will get the answer. Okay, the thing is all of the values already given in the question except the value of JA. So the value of JA actually you already calculate in the question A. Okay, so you can use the value of JA, flux of A, which is NH3. You can use this value as your JA because JA value is the same value upon the length, whatever length that we apply in the tube. So you can use this value to substitute into the in this JA equation to find out the value for PA3. The rest of it you get the question already give you the information. And finally, you will get the value for PA3, which is 13.33 kPa. Okay, but yeah, of course, you need to see the standardization of the unit first. Like for let's say for 1 feet, okay, the R constant is in maybe in meter. So you need to either you want to pick the R constant which is in feet, or you need to do the unit cancellation first. But let's say if you want to use this as your R, so meaning the Z value from the question from feet 1 feet, you need to convert it to be in terms of meter first. So convert feet to meter by using this equation, this unit conversion, and then after you get all of the unit standardization, make all of the unit standard for all of the values, then you can press your calculator to find out the value for PA3. Okay, so that's how we solve for the question 3C. Alright, and last but not least, question number 4. Okay, ammonia gas is diffusing through nitrogen gas under steady state condition with N2 non-diffusing. So this case study is refers to the one component diffusion, where the keyword is non-diffusing and another keyword is insoluble. So this case study is refers to not to equimolar contour diffusion, but it refers to one component diffusion. And the first chemicals or component is ammonia gas, so this will be component A, and nitrogen gas will be your component B. And they give you the total pressure, of the system is 1.1 times 10 to the power of 5 Pa, and the temperature given is 298 K. Okay, and the partial pressure of component A, which is NH3, is being given, which is 1.33 multiplied with to the power of 4. So this will be Pa1, and the other 0.20 meter away. So this is the Z, and then this is the Pa2. So if you cannot imagine the location of all of the values, you may draw the illustration like what we have practiced in the question number 1 and question number 2 previously. Okay, so and then one more information is about the diffusivity coefficient. They give you the value of DAB. Okay, and then the first question for question number 4, calculate the flux for NH3, which is the flux for one component diffusion or non-diffusing component is denoted as N. Okay, N. So this will be NA because NH3 is component A. So by referring to the appendix, the equation used to calculate flux for one component diffusion is according to the second equation in the principles of mass transfer, chapter 1. Okay, which is you write down again this equation in your answer script. And A is equals to DABP, PA1 minus PA2 over RT, Z2 minus Z1, multiply with P minus PAM. Alright, so we need to calculate NA with refers to that case study. And as usual, we know that in order for us to find out the value of NA, we need to identify all of the information for this equation. So based from the question already gives you the value for DAB, pressure total, PA1 and PA2. R we can get from the appendix. T already given in the question. Z also given in the question, which is, what's the value? 20 meter. And then this one, okay, this part. So this part you need to solve first before you substitute all of the values inside this equation. So P minus PAM, P minus PAM already being stated in the appendix, which is this equation, okay, the last equation in chapter 1. Okay, the last equation in chapter 1. Okay, rewrite this equation on your paper. Okay, and then solve this equation first, which is you need to substitute all of the values inside the PA1 minus PA2 ln period pressure total minus PA2 divide with pressure total minus PA1. Okay, don't forget to put the bracket in the calculator, because if you are not putting the bracket in sufficient values of sufficient bracket in your calculator, then your maybe your calculation will be result the wrong value. Okay, so and please don't forget to write down the value of the pressure together with the units and shows the unit cancellation. And if you can recall back what I've explained in the class, this log mean pressure contain unit. So the value later on, you get the value here and you will get unit pressure, because when you cancel out the unit for this one, for let's say this is ATM, and then the remaining, the top equation, okay, it contain of another unit, so this will be ATM. So the final answer is the value with the unit pressure. So after you get the value, okay, for P minus PAM, you substitute inside this equation, then finally you will get NA value. So that is how you solve for question number A. Okay, for A. And finally you will get the value of flux for NH3 3.433 multiplied to the power of 10 to the power of minus 9 kgmol per m2s. And then for B, calculate the flux for NH3 if assume that N2 is diffuse. Okay, actually for one component diffusion, they just have the value for NA, because we don't have to calculate for NB, because according to the fundamental, if the component B, which is N2, is non-diffusing, the flux for nitrogen will be automatically be zero. Okay, so that's why there is no question ask you to calculate flux for nitrogen gas under condition of non-diffusing or one component diffusion. So only you need to calculate flux for NH3, which is Na, because only A can diffuse into B. B is remain stagnant or non-diffuse into A. Right. So for the question 4B, they ask you to calculate flux for A. Okay. If assume that N2 is also diffuse. For this case study, it is N2 is non-diffusing, but for 4B, they assume when we assume N2 diffuse into A or into NH3, it makes that this statement is changed from one component diffusion to be equimolar counter diffusion, because both of the component can diffuse one into another. So what happened? Okay, we may no longer use the equation used to calculate flux by using the second equation, because the case study already changed from one component diffusion to be equimolar counter diffusion, because the N2 also diffuse into NH3. So what's the final equation that you have to choose to solve for 4B is the first equation. Okay, but the thing is for question B, calculate the flux for NH3. This will denotes as J, because the equimolar counter diffusion to calculate flux, okay, we denotes as J. So that's why you need to apply for the first equation. JA is equals to DAB over RTZ, PA1 minus PA2. Okay, so this will be PA2. So again, repeat the same steps. Okay, just put or substitute all of the values given from the question into this equation, and then shows put all of the values, and then if the values the unit is not standardized, so you need to convert it first. Okay, and then after that, put all in this equation together with the relevant units, and shows the unit cancellation, and finally put the final answer together with the last unit. Then you will get the value of the answer is 3.093 multiplied with 10 to the power of minus 9 kgmol per m2s. Okay, so that's the idea on how to solve for 4B. So altogether, okay, I already give you an idea on how to solve for all of the question regarding to the tutorial chapter 1, principles of mass transfer. So if you have any difficulties in doing this question, you may ask me personally through WhatsApp, or you may ask in the WhatsApp group. Okay, and I think it's very straightforward question, and hopefully you can get the final answer correctly. So with that, I end this presentation. So please do it at home. Okay, this tutorial question. Assalamualaikum warahmatullahi wabarakatuh.